If you try to picture the infinite vacuum of deep space, you most likely imagine complete, absolute silence. We make a similar assumption about the deepest part of our own planet. The Mariana Trench drops down nearly 7 miles beneath the ocean's surface, an abyss completely cut off from the world above. But in 2003, astronomers detected a genuine acoustic wave radiating from a supermassive black hole in the Perseus galaxy cluster, roughly 240 million light-years away. 12 years later, researchers dropped a microphone into the absolute bottom of the Mariana Trench, the Challenger Deep. They captured a chaotic roar of acoustic energy. Scientists originally ventured into both of these extreme environments, hoping to establish a baseline of absolute silence. The audio they recorded instead proves that the voids of our universe are surprisingly loud. This chart maps the depths of the Challenger Deep against the crushing weight of the water above. At 36,000 feet down, the pressure reaches a staggering 16,000 pounds per square inch, more than 1,000 times the atmospheric pressure of a standard room. In 2015, the National Oceanic and Atmospheric Administration, working with the Coast Guard and Oregon State University, deployed an instrument into this trench. Their goal was to record the natural ambient noise floor of the deep ocean. To survive the descent without imploding, the team had to wrap a ceramic hydrophone in a thick titanium casing. They lowered it at an agonizingly slow pace of just 5 meters per second into the water. When they retrieved the flash drive weeks later, they didn't hear silence. They heard the overwhelming clamor of a Category 4 typhoon that had passed directly over the drop site. Embedded in those same recordings were the low moans of baleen whales and the distinct mechanical whine of commercial shipping propellers passing near Guam. This diagram illustrates how the extreme density and pressure of the deep ocean actually work together to create a hyper-efficient conductor for acoustic energy. Instead of dissipating, pressure waves from the surface travel downward, retaining their structure for miles. The deepest trench on Earth doesn't insulate itself from the surface. It acts as an acoustic funnel, trapping and amplifying the chaos from the world above. A similar acoustic phenomenon happens deep in space. Take the Perseus galaxy cluster, located 240 million light-years from Earth. For decades, the idea of sound traveling across deep space presented a physics problem. Sound is a pressure wave. It requires a physical medium to ripple through, which seems physically impossible in a vacuum. This visual overlay reveals the hidden medium. The seemingly empty space between the galaxies in the Perseus cluster is actually filled with massive clouds of hot gas, reaching temperatures of 50 million degrees. That gas provides the acoustic medium. Using the Chandra X-ray Observatory, NASA didn't try to record audio directly. Instead, they used the telescope's X-ray optics as an ear to visually photograph the pressure ripples moving through the hot plasma. This animation tracks massive sound waves as concentric pressure ripples pushed outward by the central black hole. If you were to map them to a musical scale, they represent a B-flat note sitting roughly 57 octaves below middle C. It has been humming at that exact pitch for 2.5 billion years. This frequency graph shows the data sonification process required to hear it. Scientists scaled the original cosmic B-flat wave up 57 to 58 octaves, more than 144 quadrillion times higher than its natural pitch, to make this subaudible frequency perceptible to the human ear. We lack the biological hardware to hear space naturally. By using X-ray optics to photograph the physical footprint of acoustic energy, we can translate those visual ripples back into an audible format. These recordings provide practical data. The Mariana Trench audio establishes a crucial baseline to measure how human-caused noise pollution penetrates and affects deep marine ecosystems. In space, sound waves echoing through the Perseus cluster carry tremendous energy, roughly equivalent to 100 million supernovas, physically heating the surrounding cluster gas. For years, astronomers couldn't explain why this dense central gas didn't rapidly cool down and collapse into trillions of new stars. The acoustic heating from the black hole provides the exact physical mechanism needed to prevent that cooling flow. The most desolate voids of our universe are not silent. By engineering new ways to listen, from dropping titanium hydrophones into ocean trenches to pointing X-ray telescopes at distant galaxies, we have found a universe constantly humming with hidden energy.